So we have our file here for Bob that's been encrypted with AES and a strong password, but how do we get that password to Bob so that he can decrypt it? It's not much good sending the password with the email, so we could send it via another method. We could send it via an out-of-band method by maybe calling him or sending him a text message, but that's just not scalable at all. It's just not usable as a real-time encryption method, which brings us to the other type of encryption algorithms, and these are called asymmetric encryption algorithms. And this is because they use two keys as opposed to one key. And asymmetric is also referred to as public and private key. And public and private are the two keys that are used in asymmetric encryption. So we have symmetric encryption, one key, asymmetric encryption, two keys, the public and private key. Some very smart people invented this public and private key encryption and the algorithms based on the difficulty of certain mathematical problems. I won't go into the details of the mathematics, as understanding it isn't required to keep you secure. You just need a basic understanding to make the right choices about the algorithms and the strength of the algorithms and the crypto systems that you're going to use. So the following are examples of asymmetric keys that you will see. The first one is RSA, and this is very common, one of the most common asymmetric algorithms that you will see, and I'll show you where you see them and how they're used. The security of the algorithm comes from the difficulty of factoring large numbers into their original prime numbers. Another common and increasingly popular algorithm is the elliptical curve crypto system, or ECC. Security of this algorithm comes from computing discrete algorithms of elliptic curves. There's Diffie-Hellman, and the security of this comes from the algorithm calculating discrete algorithms in a finite field. Diffie-Hellman is becoming more popular because it has a property called forward secrecy, which we'll discuss later. And then you've got Elgamal, and the security of this algorithm comes from calculating discrete algorithms in a finite field as well. These asymmetric algorithms help solve the problem of exchanging or agreeing keys, and also allow for something called digital signatures. So we can potentially use public and private keys to send Bob our secret key securely without anyone intercepting it. As I said, with public and private key algorithms, instead of there being just one secret key, there are two keys. But in this case, there are the public key that is designed to be known by everybody, i.e. it's public, and the private key, which should be kept secret at all times or private. Now, these keys are mathematically related, and the two keys are generated at the same time. They have to be generated at the same time because they are mathematically related. Any website that uses HTTPS, for example, has a public and private key they use to exchange a symmetric session key to send you encrypted data. So it's a bit like the zip file that we've seen. They use these public-private keys, and then they need to send another key, like the key we're using for the zip file, in order to do the encryption. So in asymmetric encryption, if a message is encrypted by one key, the other key is required in order to decrypt that message. If you encrypt with the private, you need the public to decrypt. If you encrypt with the public, you need the private to decrypt. It is not possible to encrypt and decrypt using the same key, and that's crucial. You always need the counterpart key to encrypt and decrypt. But why should you encrypt with a public or private key? What's the difference? What's the point of using them? Why not just use one of them? Well, let me explain the usefulness of these and how they can be used. So, if you think of yourself as the sender, and the sender is encrypting with the receiver, Bob's public key, this means you're wanting privacy or confidentiality, so no one else can read the message but the receiver. So you encrypt the file with the receiver's public key. The message can only be decrypted by the person who has the corresponding private key, or Bob's private key. The receiver, though, cannot confirm who has sent it, that you have sent it, i.e. there is no authentication because anyone can use Bob's public key to encrypt. So when the sender encrypts with the receiver's public key, the message is confidential and it can only be read by the receiver who has the private key to decrypt the message, but there's no guarantee of where that message came from. And that brings us to the second way of using these public and private keys. So if you encrypt with your own private key, then this means authenticating is what you're interested in. It means it's important to you that the receiver knows that it is you that has sent it. So you would encrypt with your private key. This provides assurance to the receiver, Bob, that the only person who could have encrypted the data is the individual who possesses that private key, your private key. Encrypting data with the sender's private key is called an open message format because anyone with a copy of the corresponding public key can decrypt the message. So you can think about it like you're putting something officially on the internet for everyone to read, and because you've encrypted it with your private key, everyone can confirm that you have genuinely produced that. Confidentiality or privacy is not assured in this case, but authentication of the sender or you is. Now, when various encryption technologies are used in combination, such as the ones we've talked about, because these can all be used in combination and not used in isolation, they're called a crypto system. And crypto systems can provide you with a number of security services. And some of these services are confidentiality, which is privacy, authentication, which is knowing that Bob is the real Bob or you are the real you, non-repudiation, which means you cannot later deny that you sent or encrypted a message, and integrity, that the message hasn't been altered in any way. Examples of crypto systems include anything that uses this encryption technology, so PGP, BitLocker, TrueCrypt, TLS, even BitTorrent, and even the example of WinZip that we use to encrypt that simple little file. So for us to send Bob our file, we can use Bob's public key to encrypt the file, or we can use it to exchange the password for the zip file. But we would, of course, first need Bob's public key. And we'd only need to receive this public key once in a secure manner, and that's important, and we could then forever send messages encrypted just for Bob to read. And PGP is an example of something that does this. That's an encryption technology for email. But you might ask yourself, well, okay, why don't people start to use this for email? Why isn't PGP used for email? Well, it's because exchanging the keys is a little bit of a tricky task, and it's also not easy for people to understand this. So that's why encryption within email has not been adopted. And actually, email itself is pretty broken because it was never designed for security. But back to encryption. So when it comes to public and private key cryptography or asymmetric encryption, there are some strengths and weaknesses. With public and private key, you have better key distribution than you do with symmetric systems. So Bob can place his public key on a site or his website, and anyone can send him encrypted messages or data to him that only he can read. If you use a symmetric key and want to send your zip file to Bob and say 10 other people, you need to give your password to 10 people. That's just not scalable at all. So asymmetric algorithms have better scalability than symmetric systems. Public and private key also provide authentication and non-repudiation, but the weaknesses are that, unfortunately, these encryption algorithms are actually very, very slow compared to symmetric systems. If you look at the bit length after asymmetric algorithms, you'll notice that they're a lot higher than they are for symmetric key encryption algorithms. And this is an indicator of how much slower they are. It's back to the analogy of the number of locks on the door. With public and private key, there are many more locks on the door, so it takes much longer to encrypt and decrypt. So it's mathematically intensive for the CPU, which is why we have something called hybrid systems or hybrid crypto systems. Public and private keys are used to exchange and agree keys, and we use symmetric algorithms like AES to actually encrypt the data. So therefore, we get the best of both worlds. HTTPS using TLS and SSL is an example of this type of hybrid system, and so is PGP. And we'll talk about HTTPS and TLS going forward.